Hi. In the previous video, we found a particular solution for a second order difference equation with constant coefficient and constant term. Of course, the next natural step is to find the complementary function, that will tell us what is happening when variable is out of the equilibrium. Okay, so look. As we always do, in cases of finding complementary function, all we need to solve is the homogeneous equation. Homogeneous, of course, in a sense that on the right hand side we do not have any term, just 0. And look, we remember how we did this in case of differential equation. Look, we were using again triad solution. And look, our triad solution before, in case of first order difference equation, was this. So, if it worked there, why wouldn't it work now? Let's try. Of course, we need to remember that with this, we've got the yt plus 1 is equal to abt plus 1, and yt plus 2 is equal to abt plus 2. Okay, and now, look, we can check if it works, and we can substitute it into the equation. So we've got abt plus 2 plus a1 abt plus 1 plus a2 abt. And this whole thing equals to 0. Look, we clearly see that we can take the common part out. Definitely a. However, we can also take bt. And then we've got abt times b squared plus a1b plus a2 equals to 0. Right? Again, this is the very same trick we used in the context of differential equations. And look, again, we know that abt can never be 0. Right? So, the only thing that we've got left is characteristic equation. Now, this characteristic equation, of course, b squared plus a1b plus a2 can be solved, right? What do we get? What do we get when we solve a characteristic equation? Well, we get characteristic roots. And look, again, we've actually entered a realm we know very, very well. Look, as it turns out, everything that we learn about second order differential equations can also be applied in the case of difference equations. Okay, and look, if we have characteristic equation and we are trying to find the characteristic roots of this equation, we will encounter the three cases. The three cases, of course, are the case of real distinct roots, real repeated roots, and complex roots. Okay, because in case of complex roots, we will have to use here a new trick. For now, let's focus our attention on the case number 1. The case number 1 is simply distinct real roots. Distinct real roots. Okay, look, in this case, complementary function is going to be A1 B1 T plus A2 B2 T. Of course, encountering this case requires that expression in the under square root, so A1 square is bigger than A2. However, look, this expression is clearly a combination of what we had in case of difference equations. I'm talking about BT and differential equations. So I'm talking about the two outcomes that we simply add up. Okay, so maybe let's just do an example that will allow us to understand how to deal with this, because look, there's not much new over here. As you see, we found this very, very easy. So our example goes like this. Yt plus 2 plus yt plus 1 minus 2yt equals to 12. And we've got two initial conditions. Y0 is equal to 4 and y1 is equal to 5. Okay, so first thing, we should, let's first check if this is the case of real distinct roots, right? Our A1 squared is equal to 1, right? And this is clearly bigger than negative 8, so for A2. So definitely, this is the case of real distinct roots. Okay, so how about our solutions, right? We had negative A1 plus minus A1 squared minus 4A2 over 2. Right? So it gives us negative 1 plus minus square root of 1 square root of 1 minus square root of 1 is still 1 minus 4a2, so plus 8, okay, and over 2. This gives us two solutions. The first one is negative 1 plus 3, which is 2 over 2 is 1. And the second one is negative 1 minus 3 over 2, which is negative 2. So those two are our solutions. So the complementary function in this case is A1. Okay, we can just leave it as A1, right? Because 1 to the power of t, this is it. And then we just get A2 negative 2 to the power of t. Right? That wasn't that bad. Okay. However, the next thing we need to do, just like before, is of course to find a complete solution. So first thing we're gonna do next is to particular integral for our particular solution for our equation. Okay? So in this case, this is C1 plus A1 plus A2. So we get that this is 12 over 1 minus 2 minus 2 plus 1. Oh, wait. I'm sorry. Look, in this case, A1 plus A2 is equal to negative 1. Okay? Right? So we will have moving equilibrium. So YP, in this case, is C over over A1 plus 2. Right? Right. Yeah. So we've got that this is 12 over 3, of course, T. So this is for T. This is the case that we had previously. So look, the time path of T is simply given as A1 plus A2 negative 2 to the power of T plus 4T. Okay, and look, in this particular case, we have two initial conditions. We know that y0 is 4, right? Okay, so now, if I'm going to substitute 0 over here, I'm going to get that this is A1 plus A2, right? Times 1 plus 0, and it's equal to 4. Okay, and then we've got the y1 equal now to A1 plus, so minus 2A2, right? We got 1, and plus 4 equals to 5. Okay, so look, we got a system of two simultaneous equations with two unknowns. Basically, we get 1, negative 2, A1, A2 equals to 4, and subtracting 4 from both sides, 1. Okay, will it have a solution? Well, this is negative 2 minus 1, it's negative 3. It's different than 0, so we definitely have a solution, and now we just need to find it. Okay, so we substitute the vector to the first column, let's call it A1. So we've got that this is 4, 1, negative 2. This is equal to negative 8 minus 1, this is negative 9. So A1 is negative 9 over negative 3. This is just 3. And A2 is 1, 4, 1. So this is 1 minus 3. This is negative 3. So A2 is negative 3 over negative 3, which is 1. And we get that the definite, that this is our general solution, and our definite solution is given by 3 plus negative 2 t plus 4 t. And look, basically, this is how we deal with the case of distinct real roots. Now, what do we do in the case we need to deal with our repeated real roots? Look, as you will learn in a second, again, what we should do directly follows what we were doing in the context of differential equations. So, we've got case number 2. So these are repeated real roots. So here we have a case where a1 squared is exactly equal to 4a2. Okay? We remember that in these circumstances, we've just got one real repeated root, and that is equal to negative a1 over 2, right? Because the expression under square root is equal to 0. Now, however, we also should remember that if real roots are repeated, in order to avoid the collapsing of the expression, what we need to add in complementary function is not only to have, we're going to call it a3 b to the power of t, but we also need to add another component, a4 t bt. And this is a complementary function. This is a complementary function for the case of real repeated roots. Okay, again, let's just illustrate it with an example. Let's just say that we've got yt plus 2 plus 6yt plus 1 plus 9yt equals to 4. Our a1 squared is equal to 36, and this is exactly equal to 4a2 times, right? 4 times 9, 36. So definitely we have real, however repeated roots. Okay, so what are those roots? Well, b is equal to negative a1 over 2. So this is negative 6 over 2. This is negative 3. Right? So the complementary function here is going to be a3 negative 3 to the power of t plus a4 t times negative 3 to the power of t. Okay, but let's finish this equation completely. Let's now find a particular solution, and let's find the time path of y. Okay, so where were we? So now, particular solution. In this case, we just use regular formula, a1 plus a2, because we see that this is going to be a constant solution, so this is 4 divided by 1 plus 9 plus 6, which is giving us 1 over 4. Yeah? No. So, time path of t is given by a3 negative 3 to the power of t plus a4 times t times negative 3 to the power of t plus 1 over 4. Okay, so look, I hope you can clearly see that we haven't added here much new things, right? Basically, all we were discussing in terms of complementary function is some form of combination what we already said about difference equation of first order and differential equations. Look, situation is going to change slightly once we move to the case number 3, so the complex roots. However, as you will see, the situation here is actually even simpler than when we talk about differential equations. video, we're going to cover the case of complex roots.